Solving spectroscopy problems using the puzzle box method, proton NMR. Have you got it? This short video quiz demonstrates and then lets you try the puzzle box method of solving spectroscopy problems. It walks you through several proton NMR problems from the spectral zoo. This quiz consists of an introductory demonstration and then 3 questions. It's meant to be taken after you have studied the material and think you understand it. During the presentation, you'll be asked to pause the video to at least try to solve the problem yourself and only then to continue. It won't be hardly as effective if you jump to the solution immediately. Okay, here we go. The puzzle box method. The method emphasizes using logic and simple rules of atom connectivity to arrive at the solution with the absolute minimum of information. The principle of 100% atom economy is enforced. That is, provided we have a molecular formula, as from high-resolution mass spectrometry, those and only those atoms will be in our structure. So those and only those atoms will be in our puzzle box. The procedure involves, in order, checking for symmetry, reading integrations to make a logical hypothesis regarding equivalent protons, making sure all the atoms are in the box, using chemical shift and splitting data to connect at least some of the groups, completing the structure, if possible, using simple logic and basic rules of allowable structures. And as an added point, this word hypothesis is really important here. At any point in the process, we may come to some conclusion that isn't possible, we can't solve the problem, and the idea here is that you can go back, trace your steps, and figure out where you went wrong in your hypothesis. What statement you made is incorrect. Okay, so this is unknown 12, C4H9Br. I'm going to do this one for you, and I'm going to do the next one for you, and then I'm going to give you the last 3 to do yourself, and then demonstrate them at the end. Okay, so our integrations here are 1, 5, and 3. First thing we want to do is add up these numbers, 1, 5, and 3, and make sure they add up to 9. And in fact, 1, 6, 9, right. So that's good. We have accounted for all of our hydrogens. That's very important. Next, look at this integration, and this happens sometimes. 1, that sounds good. 3, that sounds good. What the heck is 5? All right, so what we have to do is use our own judgment as to what these 2 groups, these are really 2 groups, they just didn't get split by the integration algorithm. So we have to do this ourselves. And if you think about it, 5 is either 1 and 4 or 2 and 3, and we just eyeball this and say, well, that must be 2 and that must be 3. And besides, it's kind of unlikely that you'd have 1 and 4. You might, 2 CH2s, for example. But my working hypothesis right now is that that's a CH2 and a CH3. Okay, so in my box, I get what I think I know. I think I have a CH. I think I have a CH2. I think I have a CH3, and I think I have another CH. First thing I want to do is figure out what's left and how I've done in terms of carbons and hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9. I have all 9 hydrogens. I have all 4 carbons. The only thing left is a bromine. Watch how fast we can get this structure. I like to look at splitting and chemical shift. Let's just look at the splitting here. Here we have a CH3 over on the right that's shielded around 1 that's next to a CH2. So that means the CH2 is connected to CH3. All right. What else do we know? Well, we have another CH3 and it's a doublet, so that's connected to the CH. What if I told you I'm done? Without anything else. Because basically, I have CH2. If I were to connect that to the Br, I just finished a little molecule called ethyl bromide and left another chunk that isn't finished. So I can't do that. Where can the bromine be attached? Well, it can only be attached to the CH. And then the CH has to be connected to the CH2. That's it. We're done. I didn't use chemical shift. I used a little bit of splitting information, and I have my structure. The structure is this. Okay, that's the method. We're going to use absolutely the minimum information from the spectrum that we need. We're going to start with looking at the symmetry to see if we have all the hydrogens or we have half the hydrogens or something like that. We're going to get all the groups that we think we have in this box. We're going to try to put it together. If it works, we're done. Now, we have a lot more information in the spectrum, and it would be wise to look it over a little bit and maybe even learn something from it in terms of our structure. For example, does it make sense that this H that we're referring to, I'll call it A, is this one here at 4? Well, yes, because that's a hydrogen that is on a carbon next to bromine, and that's a decent place for an electronegative atom like bromine. Okay, what about this chemical shift for the CH3? Well, that's this one, call that B, and it's a perfectly fine place. It's an alkyl CH3 attached to an alkyl CH2, and those do appear around 1. And then we have some more, another CH3 and a CH2, a little closer to the bromine, right? These two guys right in here. And these are between 1.5 to 2. Sounds pretty good. It's always good to check your data. You have redundant data in NMR spectroscopy, and use that redundant data to actually check your answer. Okay, here's another one. Let's see what we can do. Integration. Once more, we have one of these integrations that's not split. It really should be split right here. So looks to me like that's 3 total. So this is going to be, don't you think, 1 and 2. Here we have 6. Here we have 1. Here we have 2. All right. Here we go. On the right, 6 hydrogens. It's going to be 2 CH3s is my first hypothesis. Now I might notice that they're split by 1 hydrogen. I'm not going to use that information right now. Okay, we have a CH2. We have a CH. Looks like we have another CH around 2.5, and we have a CH2. Okay, let's check, see what we've got. Hydrogens, 3, 6, 8, 9, 10, 12. That's good. Carbons, 1, 2, 3, 4, 5. Okay, I made a mistake. I mean, my hypothesis. I made a hypothesis statement that's not consistent with the data. I only have 5 carbons. What's the deal? Well, you know, we have this oxygen, and if I had infrared data, I would probably be going straight to the infrared data to find out if I have an OH, because that could have been a critical piece here. And in fact, this rather nondescript peak around 2.5 is a good candidate for that. So what I'm going to do is I'm going to change one of these CHs, CH to an OH. And now I have all the atoms. This is the entire structure. There are no other atoms. The objective is to connect them. All right, so we'll take our 2 CH3s here. And we know they're next to 1. Well, we've got 1 CH. So we're going to connect each of those to the CH like that. Notice I'm not redrawing these at all. I don't need to do that. I'm just making this crazy picture with the curved bonds. And then we're going to write it out later. Okay, what do we know about that CH? Well, that would be this one, wouldn't it? And the splitting there is consistent with the fact that we have multiple hydrogens next door to it. So that's good. What else do we know? Well, looking at the other end of the spectrum, we have a CH2 that appears to be next to a CH2. So that's pretty good. That would be this. Okay, now, here's a question. Why is this CH2 way over here at 3.5? Well, isn't it because it's connected to an OH? And now there's only one place that's right here, the CH2 to the CH. And our basic structure is, all right? So now, last step is always to confirm everything that we see here in terms of the rest of the information that we have. 2 CH3s next to a CH, that's here at delta 1.0. A CH between a bunch of carbons with hydrogens at delta 1.7, looks good. CH2s, right here next to three different hydrogens. So here you go, one on the left, two on the right. The splitting turned out to be about the same because they're on a chain, and it looks like a quartet. Technically, it's a doublet of triplets, but it's just lined up enough to give us the right splitting at delta 1.5, our OH at delta 2.5, and our CH2 connected to the OH at 3.7. There you have it. All right, that was my demo. Next ones are yours. I'll do them after you try, but I want you to try the next three and see how you do. See what kind of problems you run into, and then let's check our structures together. All right? C9H12O. Pause the video and try this, and then come back. Okay, how did you do? Looking at my integration again, 5 plus 2 plus 2 plus 3, 5, 7, 9, 12. That's good. It says we have an oxygen. Again, this time I'm maybe going to look at this peak here that doesn't have much splitting at all, and my first hypothesis is going to be that's an OH. Again, if I had an IR spectrum, I would be able to look at this and immediately know if I have an OH or not. Okay, what else have we got? On the right, we have a CH3, we have a CH2, we have that OH and another CH, and we have 5 hydrogens in the aromatic range. Well, 5 is a magic number for that. That means that we have a phenyl group, 5 hydrogens on it, connected over here. Just put a little dot there. All right, what do we know? Well, who's on the OH? It's this CH over here, isn't it? So the OH is connected to the CH. CH3 over here has a triplet. It's connected to the CH2. Ha! And we're done. That was it. There's no way to put this molecule together except one way. What do you think about that? The CH2 has to be connected to CH, and the CH has to be connected to the benzene ring. All right, so that structure is this. Benzene ring, 5 hydrogens connected to a CH with an OH on it. Just draw one of the enantiomers here. A CH2 and a CH3. Now we need to check. We have our aromatic protons between about 7.2 and 7.4. We have hydrogen on the carbon with the OH around 4.5. We have an OH around delta 4.4. We have 2 hydrogens here in the CH2 as a very complex multiplet between about 1.6 and 1.9. And finally, we have our CH3 at its normal position of about 0.085. Okay, so everything checks, and we can be pretty confident that that's the correct. Okay, here's another one for you. Take a good look, see what you can do. Pause the video, get back to me. Okay, we're back. We're going to dispatch this one very quickly. First, we spot this aromatic 5 hydrogens again. That takes care of a lot. That's a benzene ring with some attachment to it. I'll draw all the H's here just so I've got them explicitly out. I've got 1 hydrogen way over here at 9. I've got 2 hydrogens at 3.4. And what else do I need? I need an O. All right, well, the key here in this spectrum is a peak between 9 and 10. That's where an aldehyde peak comes. So the way this works is this CH is part of an aldehyde, and now aldehydes are at the end of a chain. The CH2 is in the middle. There's only one way to connect this. So this structure we propose is phenylacetaldehyde. Double check. We have the aldehyde H around 9.7. Perfectly fine place for an aldehyde hydrogen. We have a CH2 coming very nice, sharp, pretty sharp peak at 3.6. By the way, if we blew that up, we would find that that is not actually a single peak. That's a doublet at delta 3.3. And this little guy over here, this aldehyde, is actually a triplet. Although we can't, I can't see that at the resolution that I have this spectrum right now. And then we have these 5 hydrogens in the aromatic, around 7.2 to 7.5. And we just call those a multiplet. Okay, how'd you do on that? All right, unknown 26, C6H12O2. Give it a try, see what you can do, and I'll show you a good trick. Okay, how did you fare? Were you able to do that? Oh, lots of tricks in here. So we don't have any integration numbers, but what we do have is the heights of these integration lines. And we can see that that's roughly 2 to 3. And we know we have 10 hydrogens, so we have symmetry here. And in this case, what we'd have is really the ratios 4 to 6, right? To add up to 10. But that's all we have. We have no splittings whatsoever. Very interesting structure. All right, let's see what we can do. Because of the symmetry, I'm going to draw a little line down this box that reflects the left side and the right side. Everything I put on the left, I have to put on the right. All right, so I believe I have 2 CH3s, right? The 6 hydrogens. At least that's my hypothesis. That's my working hypothesis. Well, one has to be on one side and one has to be on the other side, and they have to be connected identically. Same thing with the CH2s. And what do I have left? I have 2 oxygens. I'll just put them like this. And 2 carbons, like this. There, that's the structure. How do we put it together? Consistent with the data, consistent with the symmetry. Well, you might be tempted to attach the CH3 to CH2, but look, there's no splitting. It's not a triplet. And the CH2 doesn't show up as a quartet. So that can't be it. And the CH3 can't be connected to this oxygen because that would put it way over here at 3.5. You see that? So the CH3 must be connected to the carbon. And whatever I do on that side, I need to do on this side. Okay, the CH2s could be connected to the oxygen, but they actually can't be connected to the oxygen because they're not between 3 and 4. So the evidence would be that the CH2s are connected to the carbons. And you know, that leaves one option, carbonyl group. And these connected across here. There you go. That was it. 6 carbon chain, CH3 with a carbonyl group, 2 CH2s, CH3 with a carbonyl group. There you go. Chemical shift, look good? Well, we have this CH3 here and here. These two are at delta 2.0, which is perfectly fine for CH3 next to a carbonyl group. And then these 2 CH2s, now the key here is that because they are at identical chemical shifts, they do not split each other. You cannot see any splitting for hydrogens that are at the same chemical shift. So that's about 2.6, and that's a singlet. Singlet 2.0, singlet 2.6, and we're done. Hope you enjoyed that. Remember, draw a box. Using integration, account for all hydrogen atoms. Look for symmetry. Making reasonable hypotheses, add to the box whatever groups you think you see. Do not draw any bonds at this point. Ensure that you have 100% atom economy in the box. All the atoms in the molecular formula are in the box, and there are no extra atoms, no missing atoms. Okay, now it's time to connect the groups using splitting and chemical shift. You don't have to connect all the groups, just whatever ones you see. A CH3 with a triplet, showing that it's next to a CH2, that sort of thing. A CH that's around 3.4, maybe that's connected to an oxygen, that sort of thing. These are hypotheses you're making. See if you can finish connecting the structure using simple logic. Redraw your structure, checking splittings and chemical shifts. Be prepared to revise your hypothesis. If inconsistencies arise, reconsider your hypothesis. Maybe a CH2 is really two CH groups. Maybe an integration of 4 is really a CH3 and a CH, not two CH2 groups, that sort of thing. If IR data are available, make quick checks to that along the way to verify, for example, that there is or is not an OH, is or is not a C double bond O. And finally, enjoy the challenge and satisfaction of arriving at a logical conclusion. So, I hope that was helpful, and I hope you've got it.